In section 9.2, we're going to estimate the population mean. So we're going to be writing confidence intervals for the mean. First, let's talk about point estimates. The point estimate for the population mean, again, point estimate is the best estimation for the population mean, is going to be X bar. And that's our sample mean. Recall that in chapter 8, we used the following formula to calculate a z-score. Z equals X bar minus mu divided by the standard deviation over the square root of n. Since we're using a sample in this chapter, we're going to use a t-distribution. We'll talk about the t-distribution in a little bit, but it's very similar to the standard normal distribution. The reason that we're going to use that t-distribution is because when we're dealing with a sample, we're using S instead of our population standard deviation, so we're getting some extra error. To account for this increased error, we replace the z-score with a slightly larger score, that's our t-score. So that gives us a little bit more, it makes us a little bit more conservative with our estimation, which is good. Real quick, guys, if you're noticing this thing right here, just ignore that. I'm going to bring that image in a minute. So the properties of the t-distribution, the first one is that it's different for different degrees of freedom. So our degrees of freedom are always equal to n minus 1. That's our sample size minus 1. The t-distribution, just like the standard normal, is centered at 0 and symmetric about 0. The area under the curve is 1. The area to the right of 0 is equal to the area to the left of 0, and both of these equal 1/2. As t increases or decreases without bound, the graph approaches but never equals 0. So all of these characteristics or properties are the same properties that we saw with the standard normal distribution. That's not spelled right. The area in the tails of our t-distribution is a little bit greater than the area in the tails of the standard normal because we're using S as an estimator for sigma. So we're using our sample standard deviation to estimate our population standard deviation. And lastly, as the sample size increases, the density curve of t gets closer to the standard normal density curve. So looking at this, we can see 3 different curves. The first curve is with a small value of n, so that's that kind of flatter one. As we get closer to 30, we see that middle shape, that middle curve. And for a large sample size, there's our z distribution. So you can see that as our sample size increases from a small to about 30, all the way to the standard normal, or as it increases, it's approaching that standard normal. It's important to note that in order to construct the confidence interval for mean, we have to check for normality. So we have to have that normal bell-shaped property in order to construct our confidence interval. The problems may include a normal probability plot that you guys read about in 7.3, or a box plot, or both. So below, we talk about how we're going to use these to check for normality. So the first check is using a box plot. As long as there are no outliers, then we're good. Okay, we can assume that it's normal and construct the confidence interval. However, if there are outliers, we're going to assume, let me rephrase. We're going to check our box and whisker plot to ensure that there are no outliers. As long as there are no outliers, then we'll go to our second check. If there are outliers, We're going to assume that our data is not normal and we cannot construct a confidence interval. The second check, if there are no outliers, we look at the normal probability plot. And specifically its correlation coefficient. Again, this is something that you guys read about in 7.3. So that's where this table comes in. We're going to use table 6 on page A13. So using our data, we're going to find n and calculate r, just like we have back in chapter 4. And we're going to compare our correlation coefficient for that normal probability plot to the critical value in this table. If your correlation coefficient is greater than your critical value, then the data is approximately normal, and we can construct the confidence interval. Visually, the data should look linear if the data is approximately normal. So let's see how we can apply this. We're going to determine whether or not the following are normal. So for this first example, let's look at our box plot first. Since our box plot has this outlier right here, that means that we're going to assume that the data is not normal and we're done. We can't construct the confidence interval. Using the next one, our box plot has no outliers, so then we look at our normal probability plot. Now, these data points look pretty linear here, but we're going to use that table and our correlation coefficient to verify that. So for a sample size of 9, our critical value is 0.912. Since our correlation coefficient is greater than our critical value, then we can say that our data is approximately normal and we're good to go constructing a confidence interval. As mentioned previously, we're going to be using a t-distribution. So when we're looking at calculating confidence intervals, we're going to need critical values. The critical values for our t-distribution are found on table 7. The row corresponds to our degrees of freedom, and the column represents the area in one tail. Now, in table 7, we only have values 1 through 40. If our degrees of freedom are not on the table, then we're going to use inverse t. And I'm actually going to default to using the inverse t function on our calculator. I think it's a little bit easier, and it works all the time. But there is going to be some holdups with that as well. The following are the instructions for how to use inverse t on our calculator. First, you want to determine the area less than t, so that's to the left. Find your degrees of freedom. Press the second button and then vars, and that opens up our distribution menu, and we're going to select 4, which is inverse t. Then you're going to type the area less than t, then a comma, which is above our 7, and then the degrees of freedom, and press enter. Now before I move on, I want to scroll down to this note down here. Not all of our it's not on this one. Okay, let me add that here. Not all of our calculators are going to have inverse t. Okay, if you don't have inverse t, you will use the table. you'll use table 7 or you'll use a calculator online, and we can show you all of that in class. All right, so for a 95% confidence interval, find the value of t given degrees of freedom of 14. So quickly, I want to sketch this. Again, that t distribution is normal, just like, or is bell-shaped, just like the standard normal. We're looking at a 95% confidence interval, which means that we're looking at the area in both tails being 0.05. So that means the area in this tail is 0.025, and this is 0.025. I'm going to use the inverse t function. I'm going to type first the area to the left. So I'm looking at this area right here. Is 0.025. The degrees of freedom are going to be 14. And that gives me two critical values. Negative 2.145 and positive 2.145. Again, when we're using these formulas, we're only going to use that positive critical value. For the next one, again, we're using the same area in the tail, so 0.025 because it's still for a 95% confidence interval, but now our degrees of freedom are 32. So we'll go through that same function. Area is 0.025, degrees of freedom are 32. Our critical value is positive 2.037. Let's try one more. Let's try this last one using degrees of freedom 1200. When we have a really, really large sample size, hopefully you notice that the critical value is positive 1.96. It's 962, but that's really close to the same critical value that we used when we were using the standard normal distribution. The formula for the confidence interval for population mean is very similar to that of the population proportion. It's your point estimate, which we use x bar, plus or minus your margin of error. So this represents our margin of error. Notice we're using a t-score instead of a z-score, and we're using degrees of freedom n-1. The interpretation for our confidence interval is exactly the same. To answer the question, how many licks to the center of a Tootsie Pop, Corey Hyde of Siena Heights University asked 92 volunteers to count the number of licks required before reaching the chocolate center. The mean number of licks required was 356.1 licks with a standard deviation of 185.7 licks. Find and interpret the 95% confidence interval for the mean number of licks required to reach the candy center of a Tootsie Pop. We're trying to find the confidence interval for the mean, so that indicates what formula we're going to use. That formula that we had on the previous slide was x bar plus or minus t alpha over 2 times s over the square root of n. This helps me identify what values I need to find from the prompt. We need to find our sample mean. Well, it tells me that the sample mean was 356.1. We also need our sample standard deviation, which was 185.7. We need the value of n. They asked 92 volunteers. And since our level of confidence is 95%, we know alpha is equal to 0.05. To find our critical value, we also need to mark our degrees of freedom, which is n minus 1, or 92 minus 1, which is 91. Alpha represents the total area in both tails. So if 0.05 is area in both tails, then each tail is 0.025. Using our inverse t, we're going to use that area to the left, which is 0.025, and the degrees of freedom of 91. And our critical value is going to be 1.986. Now that we have all the corresponding values of our unknowns, we plug and chug. 356.1 plus or minus 1.986 times times 185.7 divided by the square root of 92. Be careful, n is still 92, just our degrees of freedom is 91. Now, again, this is two separate calculations. Go ahead and pause the video while you type this in and come back and check your answers. Our lower bound was 317.650. Our upper bound, 394.550. When we interpret this, we're using that same interpretation that we used before. So we are 95% confident that the true population mean, because now we're talking about mean, number of licks to reach the candy center of a Tootsie Pop is between 317.650 and 394.550. Again, when we're writing that interpretation, only a few things are being pulled from the problem. Our level of confidence, the parameter that we're actually estimating, what we are actually measuring, so what's our random variable, and the upper and lower bounds. For a sample of 7 states, for the number of house fires started by candles a year, the mean was 7,041.4 fires, with a standard deviation of 1,610.3 fires. Find the 99% confidence interval for the mean number of house fires started by candles a year. So we're trying to find the confidence interval for the mean, so that tells me, again, the formula. This is x bar plus or minus T alpha over 2 times S over the square root of n. Now, there's one other thing that I want to point out before we start pulling information, and that is our sample of size 7. That's a really small sample. Because it's so small, it's unlikely that it's normal. So on my stat lab, you're going to have to verify that it's normal using that box and whisk or that box plot and the normal probability plot. With that said, on any test or quiz, you can assume normality without having to run those tests. All right, so since we're going to assume this is normal, we're just going to move ahead with finding our confidence interval. So x bar from our problem was 7,041.4. The sample standard deviation was 1,610.3. We know that n is 7, which tells me that my degrees of freedom are 6. And we know alpha is equal to 0.01. If alpha equals 0.01, that's the area in both tails. So that means the area in each tail is 0.01 divided by 2, or 0.005. Using this left region, the area to the left being 0.005 and a degree of freedom of 6, we'll use the inverse t to find our critical value. Our critical value is equal to 3.707. A quick side note, again, if you don't have inverse t on your calculator, look for an additional announcement that I'll post on D2L for a link to a calculator that you can use online, and as well as we will show you how to use Table 7 in class. Plugging into my formula for the confidence interval, x bar is 7,041.4 plus or minus 3.707 times 1,610.3 divided by the square root of 7. Now carefully type this in, go ahead and pause your video, and then come back and check your upper and lower bounds with mine. The lower bound is 4,785.186. The upper bound, 9,297.614. Now, I'm human too, so there's a chance I could have made an error in some of these calculations. If there is, please just let me know. We'll go ahead and write our interpretation. Again, just exchanging those values or those blanks in that standard structure for our interpretation. We are 99% confident that the true population mean number of house fires started by candles is between 4,785.186 and 9,297.614. Please note that some of our problems may give you an actual data set. If that's the case, then you have to use your calculator, or you can use Excel to find your mean and sample standard deviation. Next, we'll look at determining the sample size needed to estimate a population mean within a specified margin of error. We have our formula for margin of error from our formula for finding confidence interval for mean, and that allows us to find the formula for n. Just like in our previous section, we're always going to round up to the next whole number when we're estimating the sample size. And also note that in our original formula, we had T alpha over 2 for our margin of error. Now we're back to a Z. So we're changing from a z-score to a t-score because we want a normal distribution, or at least approximately normal. And we don't have degrees of freedom. We don't know the sample size, so we can't use the t-distribution anyway. The college president asked the statistics teacher to estimate the average age of students at their college. How large a sample size is needed if the teacher wishes to be 99% confident and within 1 year of the true age? From a previous study, the standard deviation of ages is known to be 3 years. So how large of a sample is needed? That tells me that we're finding sample size, and since we're dealing with means, we're going to use n equals z alpha over 2 times our sample standard deviation over our margin of error squared. Now we want to find the values of our unknowns. First, to find z alpha over 2, we need to know alpha. Alpha is equal to 0.01. Again, that's equal to the total area in both of our tails. So the area in each tail is 0.005. And again, we're looking for a z-score, so we're going to use inverse norm. On our calculator. And we'll use this left tail with the area to the left being 0.005 to find that critical value. And the critical value is 2.576. We know that the sample standard deviation is 3. And our margin of error, we want to be within 1 year, so E is 1. So our sample size needed is equal to 2.576 times 3 divided by 1 being squared. Make sure you evaluate inside the parentheses and then square it. When you evaluate that, you should get 59.721, and since we're always going to round up, our sample size needs to be 60.